Hello there, my name is Andrew Bridges. I'm the President and CEO of Photron USA Inc. We are a wholly owned subsidiary of Photron Limited in Japan, the world's largest manufacturer of high-speed cameras for slow motion analysis of events that occur a little too fast for the eye to see or understand. But today I want to talk to you about some of our polarization products. So why do we need polarization products? Well, a lot of today's materials, such as the optics for cameras, such as the one I'm looking at now, or your phone, or the lenses in your VR headset, are transparent, and it's very difficult to gauge and measure the quantity in a transparent material. But if you've ever put on polarized sunglasses and looked at the windows of automobiles, you'll see they have this crazy multicolored patterns. That's basically residual stress that is induced in those windows intentionally, so that should there be an impact, they'll break in a way that is non-threatening to the inhabitants. But that's called birefringence, and the way that we measure that is that their crystalline materials are basically either isotropic, such as glass, where the light is refracted in the same direction regardless of the angle of refraction, or anisotropic, where it comes in at two different directions. Wood is a very good example of an anisotropic material, where it's much stronger with the grain than across it. Salt and calcite are very good examples of anisotropic material too, where the light enters and is refracted at two different paths, and there is a difference between these two rays, the slow and the fast ray, which we call the birefringent retardation. And we can use that to measure the stress in these transparent or semi-transparent materials or fluids. Photron's Crysta high-speed 2D polarization camera uses a photonic crystal that is sputtered directly onto a CMOS sensor, a 1 megapixel sensor operating up to 7,000 full frames per second, or over 1 million frames per second at reduced resolution. Each of these pixels in a cluster of 4 has a different polarization angle at 0, 45, 90 or 135 degrees, which enables us to extrapolate out the birefringent retardation in these transparent or semi-transparent materials. The big advantage of the Photron Crysta over other polarization cameras is that we are using an area scan as opposed to a single line source or using rotating polarizers to move. So we're able to take instantaneous high-speed data. We also offer a range of static scan systems you're probably seeing on our display here that enable us to measure anywhere from A3 sized down to microscope sized, or even in the near infrared. So here we have our Photron Crysta camera. We have a 530 nanometer light source with a circular polarizer, and what I'm going to do is just place a piece of acrylic in front of it, which as I squeeze, you can see nothing at the moment, but when I put it in front of the camera and squeeze it, you can see the birefringent retardation of the stress being induced by me squeezing it, as well as the residual stress around the drill marks. And this gives you a better idea of how polarization can help you see damaging effects dynamically in transparent or semi-transparent materials. This is Andrew Bridges at Photonics West, thanking you for your time.